Everyone, last chapter we looked at the forces that charges feel and currents feel in magnetic fields. But now we really need to focus on where the magnetism comes from. So the source of magnetism can be seen in this picture here. You can see that there are very large coils, and those coils can carry very, very high currents. So to create magnetism, what we need to do is have moving charges. So the motion of charges actually creates magnetic fields around the moving charge. And again, we can use that first right-hand rule we talked about back in the last chapter, saying that if you put your thumb in the direction of the moving charge, whether it's a drifting charge or whether it is current flowing in a wire, you put your thumb in that direction of the motion and you curl your fingers to create the magnetic field. So for this one right here, this charge is going to be heading off in this direction the entire time. So I will put my thumb in that direction and I curl my fingers. You can see that anywhere along the right side of the charge, I'm going to get magnetic field into the page. And if I keep curling all the way around on the left side of the page, I'm going to have the magnetic field coming out towards me in the form of dots. So I have magnetic field coming out towards me on the left side and going into the page on the right side. And if you keep that going around, that magnetic field is going to form loops where it goes around like this and back underneath that charge to create a magnetic field loop. So moving charges create loops of magnetism that are around them. And this is why a moving charge feels repulsion by another magnetic field, because it has its own magnetic field surrounding it. And so when two fields interact, they will warp the space around them and push or pull depending on attraction or repulsion. So the way we can calculate magnetic field strength from a moving charge is with this. This is kind of like Coulomb's law for moving charges. So for a single solitary moving charge creating its own magnetic field, you solve it with finding the magnetic field strength B multiplied by a new constant, the permeability of free space. We've talked about permittivity for electric fields. That was the ability for an electric field to set up in free space. Now this is the ability for a magnetic field to permeate free space. And if you put something in the way, then that permeability does change. But the permeability constant there is 4 pi 10 to the minus 7th Tesla meter per amp, or you can rearrange that a little bit and write it as Newton per amp squared. But that's the constant you want to use there. To find the magnetic field strength from just one single solitary charge, you take that mu0 multiplied by the charge that is moving. You take that velocity and you cross it with r hat being the unit vector, which is a dimensionless vector that is pointing in the direction of the position with a magnitude of 1. So really it's kind of just like doing QV, and you divide that by 4 pi r squared. So the magnetic field strength around single solitary charges does fall off like the butter gun. But the question here can be, what is the magnetic field at the origin because of this moving charge? So first thing you want to know is, what direction is the magnetic field pointing in with this moving charge? Well, since the charge is moving to the right, you put your thumb in the direction of current and curl your fingers around that charge. So on the top of the charge, I have magnetic field coming out towards me, and at the bottom of the page, I have magnetic field going into the page. So again, that moving charge is creating magnetic field loops around it as the charge moves. So it creates its own magnetism. So the question is, what is the direction at this location? Well, at that location, the magnetic field is pointing inwards, and to solve it, we just have to put in our values there. Let's say that this is just a proton flying at the speed they give us there, 310 to the third, in the I direction. If I want to find the magnetic field, well, we already used the right-hand rule to find direction, but you could use this cross product up here of V cross R hat. The velocity is in the I direction, and the position vector is in the negative J and positive I direction. Well, we already know that I and I are going to give you nothing, so it's I cross negative J. And you see at this location, the magnetic field's pointing in the negative K into the page. So to solve for magnetic field strength, I just have to put in my charge, my velocity, and the distance from my charge to this location, which, if you look, we're about 3 meters up and 4 meters over. Knowing that triangle, I know that I'm 5 meters from the origin there. So here is the magnetic field from this single solitary moving charge, 5 meters from the moving charge. It's 1.92 to the negative 24th Teslas. It's an extremely weak magnetic field. And the reason it's such a weak magnetic field is we don't, 1, have a lot of charge, 2, the charge is not moving that quickly, and 3, we're far away from the charge. I mean, we're meters away, we're not centimeters or millimeters close to that charge. So magnetic fields from moving charges can be solved this way, but that is a very, very weak amount of magnetic field. To create larger magnetic fields, you're going to have to do something like that. You have to do something like what Ørsted found out in 1819. When people were dealing with electricity, we also knew that there was magnetism from permanent magnets. But he accidentally left a compass near his current carrying wires, and when the switch was closed, the current carrying wire deflected the compass. You can see our setup here is a power supply. That power supply is sending current right through that wire. You can see the compass sitting underneath the wire. That current goes into a light bulb, powers the light bulb, goes into an amp meter so I could show you that there is current flowing, and back to the battery. So what I wanted to show you here is that with that wire right next to the compass, when I turn on the current, you can see that the compass deflects because of the magnetic field from the moving charges in the wire. And what I'm doing is I keep upping the currents here, and if you just keep watching those currents rise, you can see that the magnetic field is getting deflected more and more away from the North Pole. And so now I'm at maximum current. The second thing I'm going to do here is I'm going to pull that wire away from the compass. And if I keep the current constant but I increase the distance of the wire, you can see the magnetic field strength dies. We saw that a magnetic field strength from a single charge falls off like the butter gun, 1 over r squared, but what about a current carrying wire? So what we noticed is that yes, we have to increase the current. The more charge you have moving, the more you can add up all the magnetism from every single moving charge, and you create a magnetic field. The magnetic fields will grow stronger with increasing currents, but as we get further from the wire, it decreases due to the distance of separation. What we saw in the lab was that it was a direct relationship with current and just an inverse relationship with magnetic field. If you want to calculate the magnetic field from a current carrying wire, it's I over R, so current over the distance, multiplied by a constant. The constant ends up being this. It's mu 0 I over 2 pi R. I know we had 4 pi for the individual charge, but for a current carrying wire, it ends up being 2 pi. Now, if you've got this current carrying wire, which direction is the magnetic field pointing? Well, again, thumb in the direction of current, curl your hands. On the right side, we're going into the page, and on the left side, we're going out of the page. So it creates these magnetic field loops, like I just drew here, around the current carrying wire in this direction. Reverse the current, and then you got the loops going in the reverse direction as well. So one last activity we want to show here is, could we figure out the direction for the magnetic field from this, say, square loop? At each of those locations, talk to me about what's going on at each of those dots. So I'm going to color code this loop. I'll call this wire my green wire. I'll call this my pink wire. I'll call this the blue wire. And across the top, we'll call this the yellow wire. So I'm going to look at the magnetic field from each of those wires independently at those 4 dots that I've given you there. So let's start with the blue wire. The blue wire, put your thumb in the direction of the current, and you get magnetic field into the page over here. So I have magnetic field out in the middle of the loop here, and I have a magnetic field in on the right side. That's from the blue wire. The magnetic field at the center would be a lot weaker than the magnetic field that's closer to the wire itself. Let's look at yellow, and you get into the page up top, and right through the middle there you get out of the page. You get magnetic field coming out, magnetic field out, and magnetic field out. Let's go with the green wire. With the green wire, put your fingers in the direction of current, and you get magnetic field into the page on the outside here, and magnetic field out through the middle of the wire. And let's go with the pink one. The very last one, again, fingers in the direction of current, curl your fingers to show where the magnetic field goes. It goes into the page along the bottom and out of the page across the top. It does go out of the page with this one way up here, but it is very, very weak when we get to that furthest location from the pink wire. So it looks like in the middle, all the magnetic fields from each line segment here are adding up to give you lots of magnetic field straight out of the page. It says let's try this from a side view to see what is actually happening. So if I turn this 90 degrees on its edge. At the top here, I'm going to have current coming out of the page, and on the bottom, I'm going to have current going into the page, or around the loop and back in towards the bottom. So let's make our magnetic fields. If you put your thumb in the direction of current and curl your magnetic field strength, at the top you get magnetic field to go in this direction. You get magnetic field in the counterclockwise direction. But what about the magnetic field from the bottom? From the bottom, you put your thumb into the page and you get magnetic field to form loops in the clockwise direction. So if you look at the magnetic field just at the center here, you can see that I have all the magnetic field lines pointing out towards the right. And if you look on the other side, I have all the magnetic fields coming in from the left. So really, when you have a current carrying loop, it creates kind of like a little bar magnet. I can visualize that these magnetic fields look like a bar magnet with a north pole right here and a south pole right here. You can see the lines are coming out and going up, out and going down, and on the back end they're coming in. And this is another reason to show that yes, you can't ever break up a magnet. Because magnetism creates these circular loops, you can't just slice a magnet in half and get just a north and a south, because when you do that, you still have lines coming out here and lines going in right there. You get a new north and a new south. So the examples I'd like you to try here are on this page that we gave out in class, and you can see we've already done a couple of these with the current carrying wires, the current going up or down. What if, instead of looking at the positive flow of charge, if the positive flow of charge was up in that one, that means electrons are actually flowing down. Show me where the magnetic field is with the electrons flowing in the opposite direction. Down here with the singular charges, here's a charge moving forward, and if I would draw the magnetic fields from that moving charge, again, thumb in the direction of the motion, and on my left side I can see they're all magnetic field dots coming out towards me, and on the right side I've got magnetic fields going into the page, which means they're looping up and over the top of the charge and down underneath the bottom of the charge. So they create these magnetic fields loops. Try practicing through the rest of those, and we'll do some more of these next time.